Last up in this chapter, we're talking about standard enthalpies of formation. This is just another way of calculating delta H. We already have calorimetry, we have Hess's law, we have bond energies. Our final and fourth way of calculating a delta H is from a standard enthalpy of formation. Now, standard comes from the idea of standard state. So that means that the material or the molecule or the atom is defined in its standard set of conditions. So a pure gas exactly at 1 atm of pressure, pure solids or liquids in its most stable form at exactly 1 atm, and temperature of interest, it's usually around room temperature, 25 degrees Celsius. So things like carbon, naturally occurring as a solid, specifically that solid graphite, sheets of carbon versus diamonds. Liquids, if we're talking about H2O, liquid in its standard state, H2O. A substance, if it's a solution, the standard state is 1 molar. Now, a standard enthalpy change, the delta H just looks this little different. It has that little degree symbol. It's a standardized 0 up at the top, right-hand side. This enthalpy change occurs when all the reactants and the products are in their standard state. A standard enthalpy of formation. Notice we have that little standard symbol and now an F down at the bottom right. That F, the formation, tells us that it's the enthalpy change of a reaction forming 1 mole of a pure compound from its constituent elements. Constituent elements means that the elements that form the compound are the reactants, and they must be in their standard state as well. Delta H for a pure element in its standard state is always 0. So when we see these standard enthalpies on the table, not only can we look and find the standard state of the atom or the molecule, but when we find a molecule not in its standard state or a combination of a couple atoms, not in its standard state is going to be not 0, all right, greater than 0 or less than 0. They can be exothermic or endothermic here. Now, these numbers, again, you do not need to memorize, but we do want to be able to utilize this chart. So when we're looking at this chart, what's important to note is elements are also on here as well as certain molecules, okay? We're going to write first the equation for a standard enthalpy of formation. We're going to do it first for magnesium carbonate in its standard form. So we're not going to write the delta H per se, but we are going to write the reaction. Magnesium carbonate solid is the standard state for an ionic compound. That would be the product, okay? The reactant is going to be all of the elements that composed magnesium carbonate in its standard form. Magnesium solid, carbon solid, and oxygen gas. Notice oxygen is a diatomic. Specifically, the carbon here could be determined a little bit more specifically as graphite rather than diamonds. You can just write solid. I'll expect you to note that on our chart, we're looking at graphite. Now, so to balance this chemical equation, we would do this the same way as what we had done before. We would see magnesium, there's 1 on each side, carbon, there's 1 on each side, and oxygen, there's 2 on the reactant side and 3 on the product side. So you might go through the whole rigmarole of finding the common denominator or the common multiple and then balancing the chemical equation. This is not a standard enthalpy of formation reaction. Why? Because it doesn't follow the definition. Yes, the reaction is making the molecule from its constituent elements. However, we need to have this normalized or standardized to make 1 mole of 1 compound. So we would take this reaction and divide everything by 2. Yes, it's going to look funny, but it satisfies the overall definition of a formation reaction. 1 magnesium plus 1 carbon plus 3/2 oxygen yields 1 mole of magnesium carbonate. That is the overall formation equation. Then you can go and look up the delta H of formation in the back of the textbook. It's in a really, really big chart. I would provide you that chart if necessary, if you would need it, all right? You do not need to, again, memorize any of those values. Calculating the standard enthalpy change for a reaction can actually be done. So we can either use Hess's law type of an idea with all these standard enthalpy change reactions, or we can use the idea that delta H is a state function and say that the delta H standardized for a reaction is the sum of the delta H's of formation for the components. Products are formed, reactants are broken up. So products minus the reactants, again, the sum of the products added up minus the sum of the reactants added up. The N there is because, again, coefficients are going to be utilized. So let's just take this combustion reaction, very simple, methane combustion. What we can do is, looking at the reactants and the products, look up the delta H's of formation for each of these components on our chart. The delta H of formation for methane, the delta H of formation for oxygen, the delta H of formation for carbon dioxide, and the delta H of formation for H2O. So there would be 4 values that we would want to look up. Oxygen being in its standard state ends up being 0. But let's look and see products minus reactants. We take 1 carbon dioxide and 2 waters based off of our coefficients and subtract it from 1 methane and 2 oxygens. We insert our values from the table and add them up. Negative 802.5 kilojoules per mole. That idea of overall reaction based off of the formation or reverse formation, the decomposition, can be utilized in this energy diagram that we see. If we want to understand the formation of carbon dioxide and the formation of water, but then we also have to subtract the decomposition of CH4, right? Oxygen is at its standard state, so it's 0. So overall, these are our reactants. We have to decompose our reactants, form our products, and so overall we can see the overall change of enthalpy is negative in the energy diagram as well.